Yeah, so we had seen velocity and acceleration and just about reached the dynamical equation of SHM. So let's continue from that point onwards today. We saw that if the general equation of SHM, the position or displacement with respect to mean position is given by a sine omega t plus phi, then accordingly the instantaneous velocity is given by a omega cos omega t plus phi. So from this we saw that the maximum speed is a omega and v is at pi by 2 phase difference with respect to x. And then we had seen that the instantaneous acceleration is given by this expression by differentiating the instantaneous velocity again. So from this we had seen that the acceleration has a maximum magnitude of a omega square and acceleration is at phase difference of pi. With respect to x. Now the most important thing here, connecting the first and the third equation, we had seen that acceleration, or what we can write as d2x by dt square, is minus omega square x. So this is what we then defined as the dynamical condition for SHM. That the net force F is equal to ma. So that net force is minus m omega square x, or we can write it as minus kx, where k is called the force constant. Has a dimension of force per unit length, just like spring constant. And you can see from this that magnitude of force is magnitude to displacement, is proportional to magnitude of displacement, and F is opposite x in direction. So in other words, F always points to the mean position. So it is what we call a restorative force. So just make a note of this additional part about the condition on the restorative force, or the dynamical condition. We had left off from this point last time, and we'll take some more examples from here onwards. Okay, so what this whole concept also shows is that visually we can understand it this way, that if this is the x-axis along which our object is performing SHM, and let's say this is the mean position, so at this the net force is 0. But from here, as it comes to the positive extreme of x equal to plus a, this is where there is maximum acceleration of a omega square in magnitude like this, or when it is at x equal to minus a, it is at maximum acceleration in the positive direction of a omega square. Here the acceleration is 0. Okay. Also at the extreme position, the speed is 0, whereas at the mean position, depending on which direction it is going, like this or like this, the v is maximum and it has a magnitude of a omega. And in between, if we see any other position like this, at x equal to some positive x, the acceleration will be like this, omega square x. Okay. Regardless of whatever the direction of velocity is, velocity can be like this or velocity can be like this. Okay. It could be on its way to the extreme position, it could be on its way back from the extreme position, it doesn't matter, but the acceleration will always be like this, towards the mean position. Okay. So you can see that the net force is always restorative. Okay. We have a restorative force. Whichever part of the cycle the motion is in, there is a restorative force. Just proportionate to displacement. So with proper sign convention, it becomes minus kx. Yes, I'll scroll up. So let me just see if I can minimize this so we can see the whole thing. Right.
Sir, your screen isn't visible.
Yeah, is it visible now? I've just reshared it.
Sir, it is being now it is, yes.
Yeah.
It is visible.
Okay, so let's work out a quick question now.
So just a
Okay. Okay, done.
yeah, sure. Just a minute. Done, sir.
Okay. So now example, if we have a situation like this, that given that a particle performs SHM along the x-axis with mean position x equal to 0 and amplitude a equal to, let's say, 2 centimeters, and time period, let's say 10 milliseconds. So it's a very fast kind of oscillation. Okay. So we have to find, first of all, we have to find the angular frequency and frequency, the maximum speed and the maximum acceleration. Interesting. Then we have to find V and A at an instant when x is equal to plus 1 centimeters. And we have to find x and A when V is equal to plus of V max into 3 by 5. Okay. And x is positive. Okay, so just try this out, we'll discuss. It's all based on the equations we've written above, the relationship between x, v, and a, acceleration, that is a. Okay.
Sir, time period is 10 millisecond, right?
Yeah, time period is in milliseconds. Okay, so it's 10 into 10 raised power minus 3 in seconds. In that sense, you can say it's 1/100th of a second, 10 milliseconds. So it's a very fast oscillation, as you can see. Okay, so anybody got the answers? At least frequency and omega, you can see directly how much it is. Remember, omega is defined as 2 pi f or 2 pi upon time period. Okay. Frequency is 1 upon time period. So frequency is 100 hertz. Maybe it see time period is 10 milliseconds now. So in seconds it becomes 1/100th of a second. Okay. So per second there are 100 oscillations. Yes, hope you've understood this. Okay. So omega is actually very large because frequency is very large now. It's 200 pi radians per second because the frequency is 100 hertz because the time period is 0.01 seconds. You understood, no? Okay. Now from here on, it's all formula based. Actually, everything is formula based. Use this relation. Now for the second part, you have to understand is that if x is a sine omega t plus phi, then it implies that so in general over here, x is 2 centimeters into 200 pi p plus some phase constant. P is 4 pi into cos 200 pi t plus the same phase constant in meters per second. And acceleration is or we can just write acceleration as minus omega square x at any instant.
Excuse me, sir.
Yes.
Sir, in the second question, V and A have to be found at an instant when, I mean, can you please tell
When
us
x is
condition?
equal to plus 1 centimeter second.
Okay, sir.
So at some particular instant of time, the position is at half the amplitude on the positive side, because you can see the amplitude was 2 centimeters. So when x is plus 1, that means it is midway between the mean position and the positive extreme. Yeah. So at that instant, how much will be the velocity and how much will be the acceleration?
So don't we have to put 2 centi, A in meters here?
You can put it, doesn't really matter. No? You can just write it as 2 sine omega t plus 5. It's understood that x is in centimeters.
Okay.
Okay. So see, one easy way to approach this second part is that at the instant when x is equal to plus 1 centimeter, it's at a by 2, no? Plus a by 2. Because we know that the amplitude was 2 centimeters. Okay, so that means a sine omega t plus phi at that instant is plus a by 2. So that means sine omega t plus phi was plus half. So
Sir, how plus half? Yeah, no, I got it.
So it is either pi by 6 or 5 pi by 6, or in general 2n pi plus pi by 6, or 2n pi plus 5 pi by 6. Okay, this is the general solution for omega t plus phi. So therefore, at the same instant, V is how much? It is a omega cos of omega t plus phi, where omega t plus phi now is this kind of quantity, this or this. So cos of pi by 6 is root 3 by 2. Cos of 5 pi by 6 is minus root 3 by 2. That is the same thing as the general solution 2n pi plus pi by 6, or 2n pi plus 5 pi by 6. So whenever sine theta, basically when sine theta is half, cos theta will be either plus or minus of root 3 by 2. That's the idea. So therefore V will be plus or minus of root 3 by 2 a omega. So V could be either going in the positive direction or negative direction, but it will be equal to root 3 by 2 times that maximum speed which we saw, which was how much? It was 4 pi, right? In meters per second. So V is equal to plus minus of 2 root 3, or 2 root 3 pi rather, meters per second, at the instant when x is how much? Plus 1 centimeters. So this becomes a solution to this part. Okay. Now similarly work out the logic for how we'll calculate acceleration at that instant. So this is when x is equal to plus 1 centimeter. Now use this exact same method to also figure out what will be the acceleration. Acceleration is actually easier, okay, because there's a more direct relationship for acceleration. Yes, very good, Antresh. That's correct. So you can see that for the acceleration, you can directly use the relation that it's minus omega square x. Okay, so it is if I want to express it in meters per second square, which is a good idea here, you will see that the acceleration is minus 4,000 meters per second square. You can even express it in kilometers per second. It's a second square. It's a pretty large amount of acceleration. So this is a very fast oscillating particle. Something like this happens at a scale where you have a tiny spring attached to a small particle and it's oscillating very fast inside some kind of miniature machinery, those kind of situations. Frequency of 100 hertz. For example, if you visualize the vibrations of a tuning fork, which has a frequency of 100 hertz. Tuning forks typically have frequencies of kilohertz, 2000, 3000 hertz, or 2 kilohertz, 3 kilohertz, something in that region. But something which has a frequency of 100 hertz, the way the prongs of the tuning fork would be vibrating. Of course, the amplitude is a lot less. It's not 2 centimeters for a tuning fork. The amplitude would typically be in a fraction of a millimeter. Anyhow, so this is about this. Okay, so here the visualization part also should be clear to you. So what's happening here is that if this is our general diagram and this is our mean position, okay, this is our x equal to plus a position, then when our oscillating particle is located at plus a by 2, it could be going in this direction or it could be going in this direction, whichever. So v could be plus or minus, but it's root 3 by 2 a omega. And accordingly, but the acceleration will have to be in this direction, whether it's going away or towards the mean position. The acceleration will have to be minus a omega square by 2, because acceleration has the relation that it is minus omega square x. So at x equal to plus a by 2, this is what will happen, this equation. Okay. Now similarly, let's work out the last part of the question. This third part, just quickly try to work it out. Now that you understood this trick of solving, this should not be too difficult. Yes, Arvinda, very good. That is correct. Okay. But only one thing that x is given positive, so correct. So it's 8 by 5 centimeters. Very good. So V is equal to 3 by 5 A omega, no? Because V max is A omega. So that means that cos omega t plus 5 is equal to plus 3 by 5. Okay. So that means sine omega t plus 5 could be
4 by
either
5.
plus or minus 4 by 5 in general. So, but x is given positive. So that means x must be plus 4 by 5 A or plus of 8 by 5 centimeters. Okay. And when x is this much, acceleration will be minus 4 by 5 A omega square. So it will be minus of 4 by 5 into 8,000 meters per second square. So this is a situation when V is equal to plus 3 by 5 A omega or V max and x is positive. Yes, very good. That's correct, Arvinda. Yes, very good. Ansh, that's correct. Okay. So when you work this out, this will be minus 6,400 meters per second square. So this is the value of acceleration and this is the value of position at an instant when this condition is satisfied. Okay. So this is like typical example of what we call kinematics of SHM type of problem, because we are dealing with velocity, acceleration, position, those kind of things, not really dealing with force. So not a dynamics problem. So we are coming to dynamics very soon, but just before that, we will also see the next important thing in terms of derivation and formulae, the relationship between the amplitude and phase constant with what we call the initial
Excuse me, sir.
conditions. Yes.
So sorry for interruption. Can you please take it a bit up?
Just
Actually,
a moment.
I've landed in a country.
I'll go back. Okay.
Okay.
Initial conditions x naught. So x naught is the value of x at time t equal to 0. That is initial position. Okay. And like that, v naught is the value of v. Just note down this line, then we'll go back up. Okay. At t equal to 0 or initial velocity. So the relationship of amplitude and phase constant with respect to initial position and initial velocity. So this is a very important aspect of the SHM problem solving part. So we'll discuss about this. Okay, so I'm just going back to the earlier section once, then we'll come back to this. So you want to note down the second part or the third part?
Sir, the third part.
Third part. Okay.
Sir,
so
not note down. I just wanna see one thing. I mean, I've landed
so the third part is here, beta. It's on the side, on the left hand side. Yeah.
So the value of A is minus W square sine square theta, right?
No, sine beta.
Oh, okay. So actually, I took it as sine square, so that's why I got it wrong.
I understood. It comes from 2 times differentiation of sine omega t. So double differentiation of sine omega t plus 5 will give you minus omega square sine omega t plus 5. So that's how we get the relation that acceleration is minus of omega square into x. It's directly proportional to displacement, but opposite in direction.
Yeah.
So that is why when your displacement is at half the amplitude, your acceleration will have to be at minus half of omega square into a, no? Because the proportionality is omega square, but with a minus sign.
Done, sir.
Okay. Okay, so let's come to this next part now. So as I was saying, extremely important concept here. The relationship between the amplitude and phase constant with respect to the initial conditions, that is the value of the initial position x0 and the initial velocity v0. Okay. So for any SHM, for an SHM given by the equation x is equal to a sine omega t plus phi, we've already seen that the velocity is given by this relation now. So according to these above equations, it means that at time t equal to 0, that is initially, according to the equation above, the position should be a sine phi. If you just substitute the value of t as 0, so according to that, and the velocity, again substitute t equal to 0 in the velocity equation, so it is a omega cos phi. So this is showing you that there's a relationship between amplitude and x0 and v0. Okay, and there's a relation between phase constant. Now to derive that equation exactly, what we can do is from equation 1 and 2, we can apply the condition that sine square phi plus cos square phi is equal to 1. We can apply that identity. So we have x0 by a whole square plus v0 by a omega whole square is equal to 1. So this will give us the relationship that we are looking for. The amplitude in terms of the initial conditions. So this gives us the relation that the amplitude in terms of initial position x0 and initial velocity v0 is given by this relation. Okay. And likewise, to get the phase constant, we can just divide the equations. So if we do equation 1 divided by equation 2, we will get x0 by v0 on this side is 1 by omega tan phi. So what we can say is that phi is tan inverse of x0 by v0 into omega. So there is this kind of relationship between them. So the easy way to remember this relationship is also like this, that if you draw a right angle triangle which has the base as x0 and the perpendicular as v0 by omega, so you can automatically see that the hypotenuse of that becomes the amplitude. Okay. And this angle becomes phi. So this is another way to understand. This triangle represents the same information that we got in these formulae. So that is the relationship between x naught, v naught, and a and phi, okay, which, as I told you, is something important within SHM. Just make a note of this quickly, people. Then we'll see applications of this. This is very important. And from that point, we can move on to the second part of SHM, which is the dynamics part. Okay, so let's look at an example. Now we have this situation given to us that, let's say, the information given in the example is visual, that a particle is performing SHM between this position, which is the mean position, okay, and here, and here. So it is doing SHM with a time period of, let us say, 2 seconds, okay, and at t equal to 0, it is over here having a velocity like this, such that at t equal to 0, the initial position, let us say, is plus 1 centimeters, and the velocity is plus root 3 pi centimeters per second. So we have to find omega, amplitude, and phase constant. Okay. Write the equation of SHM. Okay. And find the earliest time when x is equal to plus a and x is equal to 0 and x is equal to minus a. What are the earliest times when it is at the positive extreme, at the mean position, and at the negative extreme? So just work this out, people. Yes, correct. All three values are correct for omega, amplitude, and the phase constant. So just work out the second part now, the second and third part. Yes, that's correct. So basically, once you got the first three things correct, the second part is all right. You have to just substitute in the standard equation. Now use that equation for the third part so that you can find the earliest time, right, when x is equal to plus a, or in this case, it will become plus of the value you've got for amplitude. Yes, good. Yes, your other two answers are also correct. 1/6 of a second and then 5/6 of a second. Okay, so let's just solve this out for everybody now. So you can start with the understanding that time period is 2 seconds, means omega is pi radians per second in SI units. Okay. Frequency, if you like, is 0.5 hertz. Do not required over here. Okay. Now we come down to the formula. Once we actually here we have omega already, which was asked in the first part. So this is part of the first question only. Now we come to the formula part, that if the initial position and velocity are known, then we can always calculate the amplitude using this relation. So now we need not convert to SI units, because we can see that this is 1 centimeter and this will become √3 pi centimeters per second divided by omega, which is given to us, which we got as pi radians per second whole square. Okay, so when we solve this out, units wise, this will be 1 centimeter whole square plus √3 centimeters whole square, because remember, radian is a dimensionless unit. Okay. So quite simply, you can see that this is becoming 2 centimeters. So this is in fact the same thing as what we are discussing in the previous question. When x is plus a by 2, v can be plus or minus √3 by 2 a omega, that kind of situation it is. Okay. And we can also use the relation that phi is tan inverse of x naught divided by v naught into omega. So that is here tan inverse of, again, centimeters per second. So centimeters and centimeters cancel out. So we don't need to convert that to, so it's basically just tan inverse 1 by √3. So that is 5 by 6 or 30 degrees. Okay. And now based on these values, all you have to do is set up the equation for the second part. So x is equal to 2 sine pi t plus 5 by 6. Okay. Or a sine omega t plus 5. This is the equation of SHM. Now from this, try to figure out the third part. The earliest time when x is equal to plus a, that means plus 2 centimeters, or when x is equal to 0, that is at the mean position, or at minus a, or at the negative extreme. Okay, so now this is that kind of trick we had discussed that day again. Okay. Where we had seen those graph-based problems. So we had seen that when I want x to become plus a, so in basic terms, it should become plus 2 centimeters. Here it's understood that x is in this equation, x is in centimeters, t is in seconds, because that amplitude is 2 centimeters, no? And omega is pi radians per second. So basically my sine pi t plus pi by 6 should become plus 1. So pi t plus pi by 6 should be basically pi by 2, 5 pi by 2, and so on and so forth. 2n pi plus pi by 2. This is the general solution. So this will correspond to the earliest time. Okay. So now you have to just solve this. Okay. So pi t plus pi by 6 is pi by 2. So that means, so you can just solve it like this, that t in seconds will just be 1 by 2 minus 1 by 6. Okay, so that is 1/3 of a second, or approximately 0.33 seconds. So this is the answer to the A part. This is the earliest time when this becomes this much. Okay. Now for the next part, you don't need to do a calculation, because you can see that from x equal to plus a to x equal to 0, the minimum time taken is 1/4 of time period. Okay, so that is half a second here. So therefore, t will be 1 by 3 plus 1 by 2 is equal to 5 by 6 seconds when x is equal to 0, earliest. So this is, in my mind, the quickest way of solving it, but you can also solve it this way, that when omega t plus phi in general becomes pi or 2 pi or general, any n pi, that is when x is equal to 0. So earliest is when omega t plus phi should become pi. This is the earliest time. And likewise, the C part is add another quarter time period from x equal to 0 to minus a now. The minimum time is another quarter time period. Okay. So the time should become 5 by 6 plus another half second. So what is it? 4 by 3, is it correct? No, sir. This will become 5, yeah, 8 by 6, 4 by 3. That's correct. This is the earliest. And you will see that at this point of time, omega t plus 5 will actually become 3 pi by 2. Okay, so hope this is done, people. Yeah, Tantresh, you've written this down. Very good. So this is all the first part of SHM, which is about the kinematics of SHM. Now we come to particular systems where we understand through the type of force available in the system and SHM is happening. So we're talking about forces. So we are coming to what we call the dynamical condition, or you can say dynamics of SHM. So dynamics means we are dealing with forces. So we are talking about what type of force will give us SHM. So to answer that question, we've already seen that if we have a situation where F is equal to minus kx in a 1D system, obviously along x-axis. So we can see that it means that d2x by dt square is minus omega square x, where omega square will become k by m, where m is the mass of the body on which the net force F acts. So this is basically the dynamical condition, the one we've written above, that F is equal to minus kx, because that implies this, and then this implies automatically that x is equal to a sine omega t plus phi, where obviously omega is square root k by m, which is 2 pi upon time period, or 2 pi f. But more importantly, the amplitude and the phase constant, they come from these equations. Okay. So this actually gives us everything that we require to solve a dynamics problem. Apart from the fact that we have to actually work out the force, that part we have to solve, that how F is dependent on x from the free body diagram of any system where this kind of situation is happening. So that force could be as a result of a single spring, it could be as a result of a combination of springs, it could be a spring mass system in a vertical situation, it could be a spring mass system in a horizontal situation, it could be because of electrostatic forces of acting on charged particles, it can be any such thing. Okay, but if the force has this property that it is restorative with respect to the mean position, and it is directly proportional to the displacement in magnitude, that is, in other words, it is minus kx, F is equal to minus kx, then it guarantees that the system will perform SHM with these kind of properties, with this kind of time period and this kind of amplitude and phase constant. Okay. So the first example of a dynamical system which does this is the simple spring mass system. So this is an entire category of SHMs that we'll be studying dynamically, that is SHM of spring mass systems. We'll see a few different cases of it. So next we'll look at SHM So we are always assuming the springs in such cases to be ideal springs, which obey Hooke's law. That is, the tension in the spring is given by minus kx, and the spring itself is massless. Okay. And we'll always assume that there is no non-conservative force like friction or air resistance or anything like that present. Okay. It's only going to be the restorative force applied by the spring, which drives the system. So the first example of that is the simple horizontal spring mass system. It's the most basic one. Okay. That is, you have a smooth horizontal surface with a rigid wall on one side to which we can attach a spring and attach the other end of the spring to a block which is on the horizontal surface, supported by the horizontal surface. So you can see the block is in equilibrium when the spring is at natural length. But the moment you disturb it from equilibrium, it will tend to have that restorative force, and that restorative force will directly satisfy this above equation, where k is nothing but the spring constant itself. Okay. So in this example, let's take the mass of the block as, let's say, 4 kilograms, and the spring constant, let's say we are taking it as, let's take something easy. So let's take it as 36 Newton per centimeter. So it's not given in SI unit, notice. Okay. and this surface is smooth. Okay. So first we will show that this system oscillates harmonically, that is as an SHM, and find the time period of such oscillations. And second, we'll invoke what we just learned earlier, that if initially the block is pulled, okay, stretching the spring by 2 centimeters and released from rest, then we want to find the amplitude and the phase constant for the resulting SH. And in general, we can write the equation of SH. So let's say this is the natural length position. So from here, if we pull the block in such a way that we stretch the spring through 2 centimeters or whatever and release it from rest, then not only do we know that it's going to perform SHM, but from the given initial conditions, we can find the amplitude and phase constant also. So that's what we'll do next. Okay. So just write down this part and we'll discuss about the solution of this problem. Yes, let's understand this question first of all. So we can see that when we displace it from the equilibrium position by x, okay, so if you have displaced this by x, the spring's length becomes L plus x. Okay, so the net force acting on the body is just the spring force, which gives it an acceleration like this. Okay, so you can see that T is equal to ma. Okay, and T is nothing but kx is equal to ma. But we can see that A is negative of d2x by dt square. Why? Because A is opposite to displacement, opposite to x displacement. So we have the equation that d2x by dt square is minus k by m x, which is our SHM equation. This is the SHM condition. Okay, and omega square is nothing but the spring constant divided by mass. Only thing is, now to get omega in SI unit, you have to convert k also to SI unit. So k will become 36 into 10 raised power 2 newtons per meter divided by 4 kg. So you'll see it will become 30 radians per second. Okay. So yes, you might have just missed out the unit. Just be careful. Otherwise, there'll be a factor of 10 raised power minus that you'll have to take care of. You have to convert this to SI unit. Okay. So k will become 36 into 10 raised power 2. Okay, so from that you can see your time period is 2 pi by omega or 2 pi under root m by k. So you should also remember this parametrically. Okay, so in this case the time period becomes pi by 15 seconds, right? So it's quite a fast oscillation, as you can see, because short time period, high frequency kind of oscillation. And this is something which is quite feasible. Like, and typical spring can have a spring constant like this. Okay, so you can see that if you have a spring of this type, attach it to a block of few kgs, 3 or 4 kgs, something like that. This is the kind of oscillation you will have in terms of time period or frequency. Okay, so that's the first part. So we have shown that it's SHF, it's harmonic, because so the first part that show that it is harmonic because you're getting the condition, sorry, we are getting the condition of SHF. And now we have found out the time period. So irrespective of what amplitude and phase constant it has, every time that time period will be so much only, the frequency will be 1 upon this only. Okay, now we come to the second part. So for the second part, we understand that x is equal to a sine omega t plus phi, where so far what we have got is omega is root k by m, which is 30 radians per second. Okay, but we still need to find out the amplitude and the phase constant. So this will come, remember, it always comes from initial conditions. That is the initial position and the initial velocity. So for that, we have to follow the instruction given in the question that initially the spring was stretched by 2 centimeters. So x naught was plus 2 centimeters and the block was released from rest. So amplitude you can see will just become 2 centimeters. Okay, and the phase constant, which is tan inverse of x naught divided by v naught into omega, will be tan inverse of an undefined quantity. Okay, so that is pi by 2. So here our equation of SHM will become like this: x is equal to 2 sine of 20t plus pi by 2. This will be our equation of SHM. Okay, amplitude is 2 centimeters, omega is 30 in SI units, radians per second, and the phase constant is pi by 2. You can also write this as cos also. So I'll just minimize this a little further. So this is the standard process that we have to follow in any type of dynamical situation. Okay, so just make sure you're clear about this. We'll discuss further. Sorry, 30t, my mistake. Yes, stage. I've written omega correctly over there, but inside this it should be, this is what we were pointing out, right? This should be 30t. Rest it's all right, no? Yeah, okay. Okay, so we will hope this question is fully clear. With that, we conclude today's session. Next time, we will look at a situation where the same kind of spring mass system could be in a vertical position. So the equilibrium position is where actually the spring is stretched a little bit because the tension in the spring has to balance the weight. Okay, and so on and so forth. Okay, then we'll see also situations where there will be combination of springs. So series and parallel combination of springs. If you can revise that from your earlier Newton's laws of motion, etc. Yeah, from H.C. Verma, you can now do questions up to about SHM chapter. You can do from the main exercise. You can do questions 1 to about 18. Okay, try out these questions. So that's it for today's class, people. Thanks for attending. Wish you all the best. Hope you have a nice day.
Excuse me, sir. 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 Excuse me.